Hello and welcome back. So far we have given a proof of the area formula repeated down here and two proofs of Sart's theorem in particular. In this video we want to talk about some consequences of this area formula and some of its not so obvious implications. The first application I want to talk about is the multiplicity function f, a, and y. Okay, this Jacobian, this determinant we see there, we talked extensively about it in my second video discussing some linear algebra. Notice that if f is L-Lipschitz, the Lipschitz constant is L, then df at x, provided that actually f is differentiable at x, maps the unit ball in Rn into a subset, so the image of this ball will not be bigger than a subset of a ball of radius L times R, so here R is 1, radius L, contained in an affine ND space. So the Jacobian of derivative at x, which is the ratio of the measure of the image of this linear map, so ball of x and 1, divided by the Lebesgue measure of the ball we started with, so x1, will be less than or equal to Lipschitz constant to power n, because a ball of radius L has volume proportional to L to power n. The proportionality constant is the same in numerator and denominator, so it just goes away. So this gives a bound on the Jacobian of the map in terms of the Lipschitz constant. Okay, so what does this then imply? Going back to the formula, if you have A inside Rn with Lebesgue measure of A finite, then integral of n f a y dh and y, recall that this is the number of points from set A which map to y by the function f. So this is equal to integral of Jacobian over A by the bounds we have above, so this will be less than integrating the Lipschitz constant of f to power n d ln x over A, and now that's just a constant number, so this will be Lipschitz constant of f to power n times ln of A, and that is finite, not infinity. So as a consequence, this function nfay is not infinity for hn almost every y in Rm. But this being less than infinity is just saying that there are finitely many points from A which map to y. So in other words, for hn almost every hn, because this integration is against hn, and in fact it's only on the image of the function f and not really on all of our m, because otherwise it's if you are off the image of f, that multiplicity is actually 0. So for hn almost every y in Rm, there are only finitely many x's in A such that f of x equals y. And that's not an obvious thing at all. The maps can do crazy things, so the overlaps are not nice necessarily, and it's only due to the area formula that we have this claim. Some examples you should keep in mind will be, for example, constant map. So what happens to going from Rn to Rm, where f of x equals the same point for every x? In this case, we have this huge Rm, but every point you pick, except for this particular point, is not mapped to at all. So the number of points from a subset A with finite measure, the number of points that map to these points is actually just empty set. Then there's 0 points. For this one point, though, there are infinitely many. Everything maps there. So one point has an extremely huge preimage, but almost every other point, in fact, has very small preimage. The more sophisticated example will be, of course, the case where Sart's theorem happened. If the rank of derivative of f of x is less than n for almost every x in A, then hn of f of A is actually 0. So in this case, the claim is trivially true because, first of all, so here we are in Rn, and then we map into Rm. This time the image is not as small as the previous example. So if you imagine this is R2, then, and here we are in R3, it could happen that you map into a lower dimensional thing, like a one-dimensional object, maybe this. I don't know how crazy your set A should be to achieve this, but anyway, in this case there are much more points with infinite preimages. So for example, the preimage of that could be one line segment from here to here. The image of another one could be something like a disconnected thing from here and here. But still, this set you see in the image is one-dimensional, so H2 almost every point is okay. So H2 measure does not even see this one-dimensional object. Great. So speaking of Sart's theorem, we can talk about our second application. As we saw in the proof, when we proved the area formula, we talk about two cases. So the part of A where the rank of the derivative is the maximum possible, the regular set, and then the set A minus A1, which is points where rank is less than n, or points where f is not differentiable to begin with. And then here we had Sart's theorem, for which we also give an independent proof, saying that hn of f of this part is actually 0. Okay, so almost everything you can claim anything about the images in this part because they're negligible from point of view of hn. For this part, you must investigate the proof again. From the proof, what we ended up with was that there exists some partitioning of the set into countably many subsets EI, measurable, such that each one, f restricted to each one, is BiLipschitz. That's kind of the best you get for Lipschitz regularity. And, well, of course, f of A minus the images of these pieces may not be empty, but it is 0. So which means when I have any arbitrary Lipschitz map from a subset of Rn into Rm, there is a bad set whose image though is very small, so I can ignore that. And on the rest of the set, I have these measurable pieces. They don't have to be connected or anything. So this could be my other EI, and on each one, the map going from here to here is suppose like this is one of the pieces, and the function f going from one of these pieces into that is BiLipschitz, and their union exhausts a minus a1. I probably said this cannot be empty. Probably it is actually empty. Anyway, I don't care. So that means ignore. Anyway, you have to ignore the null set from this part. So you have some image of a Lipschitz function. Those actually we're going to call a rectifiable, HN rectifiable sets. So such an object. Maybe it's composed of two parts. It could also have a lower dimensional piece, something like this. If your A is disconnected, of course you can have that. So this is a kind of object we're looking at if f is just Lipschitz. If it's not C1, it's not C infinity, you're not looking at smooth manifolds. There are overlaps, so this could be actually some part of it could fold onto itself again, things like that. But what this claim is saying is that if you ignore a null set, for example, these will be ignored, this will be ignored because it's not actually even n-dimensional, then on the remaining part, you can decompose it into pieces, and each piece comes from a BiLipschitz image from back there. And this shows that rectifiable sets can be defined by requiring that the maps that we use in their definition be BiLipschitz. We will talk more extensively about rectifiable sets, so I don't want to give definitions and other precise statements here. So application 3 is that by, I should call standard procedures, we can remove overlaps and then find some A prime inside A1 such that f restricted to A prime is 1-to-1, is a bijective map now, and still f of A is almost completely recovered by f of A prime. So you can hit the same image, but this time with a 1-to-1 map. And the way you start getting this is you, as in previous example, you find your EIs, you look at E1. When you look at E2, there could be a part that covers some part of the FE1 already covered by E1. And you remove just that part. The details, the technicalities are that you must make sure that you're removing measurable sets and whatnot. But ultimately, out of these EIs, doing this exclusion-inclusion stuff, you end up with a union, which could be a much smaller set than all of A1. For example, suppose A1 has two parts with exactly same images, so you lose half of A1 in this case. But what you care about is that you get an injective map whose image is still almost all of the very original image of that. So this might be useful in some cases. Application 4, I have two more to mention here. So application 4 is a u-substitution formula. And again, this is something that is never proven in the books or papers because it really follows from abstract measure theory. Once you have a formula for sets, basically for characteristic function of sets, then you can prove a similar formula for all measurable functions, because you can approximate measurable functions by characteristic functions, sums of characteristic functions. So in this case, the exact theorem or lemma, let's say, well, let's call it corollary, would be that if f from Rn into Rm is Lipschitz, and a subset of Rn is measurable, then for any function on this image, so image, again, we of course think about it as kind of a manifold anyway, that's the best our intuition can do. So for any function from fv, the image, into 0 infinity, that is hn measurable, so for any hn measurable function like this, we have, okay, so integrating phi of y, counting multiplicity fay dhny over m is equal to integrating, okay, so I want to pull back this function phi. Phi is defined on the image, so I compose with f, and when I apply x, now this is well defined. Now this will be Jacobian of dfx, and this will be dx, which means the ln of x. And that's a u-substitution formula. It tells you how to integrate on the manifold by pulling back the values onto the parameterization domain. And this, of course, agrees with what we've learned in Calc 3 and what we started this area formula series with. Except that you must check the following nice exercise. If you are parameterizing from R2 into R3, is Lipschitz, or C1, if you're giving this as an exercise to some undergrads that are not familiar with Lipschitz functions, then at points of differentiability, which is almost everywhere by Rademacher. Okay, so this is how we compute our Jacobian in all of these. dfx transpose dfx multiplied, you take determinant of the square matrix and then take root. Claim is that this is the same as taking partial 1 of f, taking partial 2 of f. There are two variables in R2, maybe uv, so this is partial u, partial v. You cross product them, which is meaningful because they are maps in R3, and then you take their norm in R3. Because this is what we are introduced to in calculus courses, and this is what we've learned in this series at least. And well, we have to calculate that these are equal, which is a very straightforward exercise. Okay, and as you can see, this formula can have some cool applications. The sixth application is that the surface measure on an embedded submanifold of dimension n inside the bigger Euclidean space Rm. So inside Rm, so Rm is larger and there's an n-dimensional embedded submanifold in it with no like crazy self-intersection and things like that. Then well, the surface measure on this thing equals the Hausdorff measure on it, where it is computed. So what metric do we put on that? With respect to the Euclidean distance induced from Rm. Yeah, so let's say we do have now a nice manifold, maybe even without boundaries. So let's say you have this torus, which is not, okay, accept this as a smooth manifold from me, and this torus is sitting inside R3. It is a two-dimensional beautiful object. Now there is a distance on this T. Given x and y, you compute their distance as if they are sitting in R3 and you just ignore T. So that's the Euclidean distance induced on this object. And with that distance function, of course, you can look at Hn. And the claim is that this Hn equals the intrinsic surface measure on the torus. I'm going to make more videos on this particular subject, so I don't want to get into details of what this surface measure is defined as in the first place. So to prove this, first you have to give a definition of what the surface measure is. But if you happen to know through your Riemannian geometry courses, where this is constructed as integrating the determinant of the Riemannian metric matrix, this Gij matrix, this measure comes from that. And if you look at the smooth parameterization of the surface and apply the area formula, and noting that it is one-to-one map, the multiplicity goes away, all of that works together to prove this. However, there's actually a direct proof for this, from which you can actually work backwards and conclude the area formula from knowing this fact up front. That is a direction we might take, but I'm not completely sure about yet, so I don't make a promise in that regard. Anyway, so these are some applications of the area formula, not all of them. These are corollaries, not even applications. So if you want to find applications, there will never be a complete list, because this pops up here and there, and it's one of the fundamental results in geometric measure theory. So hope you enjoyed this. If you haven't watched my previous videos, everything I mentioned here has already been covered by my previous videos, so please do so. And one more humble request: if you have not yet subscribed but you're following my videos, please do subscribe, so that I do know that you want more of these. Thanks a lot, and have a great day and a great happy new year.